Dear listeners, today I shall discuss about magnetic moment and magnetic dipole moment. The magnetic dipole moment is a significant quantity in electromagnetism. Let us consider a bar magnet Ns of pole strength M and of magnetic length twice L. That is, length between the two poles is twice L. It is placed in a uniform magnetic field B at an angle theta with the direction of B. Two equal and opposite forces MB and minus MB act on the two poles. One is along the direction of B and the other along a direction opposite to B. These two forces constitute a couple and thereby a torque. The magnitude of the torque tau equal to force, magnitude of the force MB, effective length, that is magnetic length twice L, into sine theta, that is twice ml b sine theta. If we place the magnet at an angle theta equal to 90 degree in an uniform magnetic field of 1 Tesla, that is B equal to 1 Tesla, then the magnitude of the torque becomes twice ml. The twice ml is called the magnetic moment of the bar magnet, and we can express the torque in terms of this quantity. It is denoted by mu equal to twice ml, and we can express the torque in terms of mu, tau equal to mu b sine theta. The vector torque tau equal to mu cross b. Mu is a vector. That is, the magnetic moment of the bar magnet is along the magnetic axis from south to north. This is the direction of mu, that is magnetic moment of the bar magnet. So we can define the magnetic moment. If a magnet is placed at an angle 90 degree to the direction of magnetic field of magnitude 1 Tesla, then the amount of torque acting on the magnet is called the magnetic moment of the magnet. The magnetic moment mu is an important vector associated with a magnet. Where there is a magnet, there is a magnetic moment. If we find a magnetic moment somewhere, then a magnet will be there. A similar torque acts on a current conducting coil in a magnetic field. The magnitude of this torque is tau equal to Nia b sine theta. N is the number of turns of the coil, I is the current, A is the cross-sectional area of the coil. It is similar to tau equal to mu b sin theta. Therefore, NIA is equal to mu. That is magnetic moment mu সমান NIA. Magnetic moment of a coil conducting a current I is NIA. The vector mu is the magnetic moment of the coil. It appears in the coil when a current flows through it. As we know, magnetism arises from an electric current. That is why a current conducting coil acquires a magnetism. If two poles of a magnet are very close to each other, then such a magnet is called magnetic dipole, and the corresponding magnetic moment is called the magnetic dipole moment. A current loop is a magnetic dipole. It is not surprising that hydrogen atom is a magnetic dipole. The orbiting electron makes a current loop, so hydrogen atom becomes a magnetic dipole, and it has a dipole moment mu of magnitude Ia. If nu be the frequency of revolution of an orbiting electron, then we may say that nu E charges are flowing in 1 second in the orbit. That is I সমান nu E. So mu equal to nu Ea. The vector mu has the direction towards which magnetic lines of force of the magnetic dipole emerges. Look at the model. It's a model of electron's orbit in hydrogen atom. Electron is moving anti-clockwise, so current is flowing clockwise, and the lines of magnetic force, magnetic field, and the magnetic lines of force are emerging forward according to right hand rule. Look at the second model. Magnetic lines of force are emerging normally to the loop surface. It is emerging forward, and the magnetic dipole moment is directed to that direction. It is also normal to the surface of the loop. The necessary centripetal force for orbiting electron in hydrogen atom is mv square by r, and it is provided by the electrostatic force on the electron by the proton is 1 by 4 pi epsilon naught E square by R square. So we have V equal to 1 upon root over of 1 upon 4 pi epsilon naught E square by mr. The period T equal to twice pi r divided by V. That is frequency nu সমান, that is frequency nu equal to 1 upon T V by twice pi r equal to root over of E square by 16 pi cube epsilon naught mr cube. Magnetic dipole moment of the hydrogen atom mu equal to E A nu. Inserting the value of nu, we may have mu equal to E square by 4 root over of r divided by pi epsilon naught m. The orbital angular momentum LL, small l is the orbital quantum number, equal to mRV, equal to root over of E square mr divided by 4 by epsilon naught. Therefore, mu by LL equal to E by 2m. That is, mu equal to E by 2m into LL. The radius of the electron orbit in hydrogen atom are equal to epsilon naught h square n square divided by pi m e square. The radius is expressed in principal quantum number. So magnetic moment mu equal to E square by 4 root over of r divided by pi epsilon naught m. Substituting the value of r, we have EH divided by 4m into principal quantum number n. When n is equal to 1, that is in the first shell, the magnetic dipole moment will be EH by 4m. It is called Bohr magnetron. Thank you.